Let's talk about what happens when we don't have sufficient sample sizes. We know how to do inference when we have a sample size greater than or equal to 30, but let's see what happens when we don't. So we no longer can use the central limit theorem, which means we can't use the standard normal or Z table. So we have to use what's called the student's t-distribution, which is also unimodal and symmetric, but it'll give more weight to the tails. And it also is highly dependent on sample size. There will actually be a different t-distribution determined by what's called the degrees of freedom, which is the sample size minus 1. So we're going to start using the t-table to see how these procedures go through. You'll still notice a fair bit of similarities. Now, we don't really have a practical way to calculate p-value. I'll show you that, particularly in an exam situation. You can use statistical software, and I'll show you a sort of a quick workaround for some of the exercises you'll see in the assignments. We generally do the test statistic against a critical value, which we'll call TA or T star A, which I believe is how it's denoted in your book. And exactly the same way we used the critical values of Z star, it is entirely dependent on our alternate hypothesis. If we have greater than, it's if T is greater than T star A. If it's less than, and if it's less than negative T star A. And if it's not equal to, we reject if the absolute value of T is greater than T star alpha over 2. And you can find them using the T table, which is included in the final exam stat tables. And I'll be using them throughout for examples. Now, if we want to compare one mean, do a hypothesis test for one sample, our test statistic is T, and you'll notice it's all exactly the same as the standard normal or Z test. X bar minus the mean under the null hypothesis divided by standard deviation divided by the square root of n, the sample size. The confidence interval is similarly constructed exactly the same, except instead of Z alpha over 2, we use T alpha over 2. And we'll see how that works. So here's a question. They're testing 20 men with male pattern baldness. We're testing a hair growing rate formula. We're given an average change in hair density, a sample standard deviation. And we want to know, is there significant evidence at the alpha equals 0.01 level of significance that we see a hair density change, but it is different from 0, or evidence that it's greater than 0? So let's focus on this first question. So we're talking about a hypothesis test because we're given a level of significance and we're testing to see if there's a difference. Our null hypothesis is talking about the variable of interest, which is the mean amount of hair regrowth. And we're testing to see, is it different from 0? So our null hypothesis is that it's not. It's different. It's the same as 0. And now we want to see, is it different from 0? And now different means we're testing in two directions, so we say not equal to 0. So our test statistic is pretty straightforward. Just T is equal to X bar minus mu naught divided by sample standard deviation divided by the square root of the sample size. So we know our sample mean is 14.4. Our sample standard deviation is 10.76. And we had a sample size of less than 30. We had only 20, which is why we're using our T procedures. So we have 14.4 minus 0. 14.4 divided by 10.76 divided by the square root of 20 is about 2.406, and that will give us 5.985. But we'll just round it to about 5.99, close enough. So now what we need to do is generate our rejection criteria, T star alpha over 2. Now, to generate this, we're alpha over 2 because we remember our alternate hypothesis that it's not equal to 0. So we'll go to the table and find that value. So here's the student's t-distribution. This is the one you'll be issued for the final. You'll notice there are 3 headings: confidence coefficient, level of significance for a one-tailed test, level of significance for a two-tailed test. So we are looking at a two-tailed test. Remember, our alternate hypothesis was not equal to. We're testing in two directions. We were at the alpha is equal to 0.01 level of significance. So we use this column, and then we go to the row based on our degrees of freedom. Degrees of freedom are n minus 1. So 20 minus 1 is 19. Here we see it is 2.861. Now, 2.861 is less than 5.99. That means we can reject H naught. We can say at the level of 0.01 level of significance, we do see change that is different from 0. Now this is a two-part question. This says, is there evidence that it's greater than 0? So this is giving us a different null alternate hypothesis. We use the same null hypothesis. Now we're saying, is the mu greater than 0? Now, our test statistic won't change. So our t is still equal to 5.99. But now we have to compare it to our t star. But in this case, we're doing t star alpha. So let's go to the table. So we're still dealing with 19 degrees of freedom, but here, rather than using the two-tailed test 0.01, we use this section for one-tailed test. We're testing in one direction to see if it's greater than or less than. So 0.01 for one-tailed test is this column. So we go to this column, and we see it's actually 2.539. So we compare our test statistic of 5.99 to our critical value of 2.539. We see it as once again still bigger, so we'd still reject H naught. We have sufficient evidence at the alpha equals 0.01 level of significance that the change is greater than 0. In this case, we have a boxer who's told by his physician he gets 3 more concussions, he's going to die. He looks over his 12-year career, notices he's had 33 concussions. He has a standard deviation of 1.3 concussions per year, and he wants to know how many concussions he's 80% confident he'll get in the next year. So he wants to develop a range of values he can have an 80% level of confidence in, which means we're talking about a confidence interval. Now, a confidence interval uses alpha over 2 with n minus 1 degrees of freedom. T alpha over 2, confidence intervals are always in 2 directions, times by the sample standard deviation by the square root of n. So what's our sample mean? Now this question doesn't give it to us exactly, but it does say he's had 33 concussions over 12 years. We know x bar is equal to x over n, 33 concussions over 12 years. That's equal to 2.75, an average of 2.75 concussions per year. So we know our sample standard deviation is 1.3. We know our n is 12. 12 years is what this sample is based off of that. So now we just need to find this t value. And that will require going to the table. So here we go to the confidence coefficient, 1 minus alpha. He wanted 80% level of confidence, so that's this first column. He had 12, an n of 12, so we take n minus 1 as 11, and we see it's 1.363. Just as an aside, one thing you might notice that's really useful with this is it has all these degrees of freedom, including all the way up to 200, but at the bottom there's infinity. And what's nice about the student's distribution, because it is unimodal symmetric very much as the standard normal, at an infinite degrees of freedom, it actually collapses to the standard normal table. So you don't need to waste space on your cheat sheet writing out the common least values, because if you need if you're doing a standard normal sufficiently large sample, confidence interval, say at 98%, you can just go down to infinite degrees of freedom and see it's 2.326. We have our t value, which we know is 1.363. So 2.75 plus minus 1.363, 1.3 divided by the square root of 12 is about 375. Generally speaking, 3 digits after the decimal place is good enough. Plus minus 1.363 times 0.375 will round to about 0.511. So that means 2.75 minus 0.511 is 2.239, and plus 0.511 is 3.261. So this boxer can be 80% confident he will have between 2.239 concussions and 3.261 concussions in the next year, which is above. You wouldn't recommend him go into boxing because this is above what the physician told him could be fatal. We're also going to see some T procedures for when we can compare two different means. So if we're comparing two groups and want to develop either a confidence interval or do a hypothesis test, we can do that. Now, when we have two independent means, meaning that they're drawn from two independent samples, two independent populations, we can develop a confidence interval, which is the mean of the first sample minus the mean of the second sample, plus minus the t, using the lowest of the sample sizes, sample 1 or sample 2 minus 1 for the degrees of freedom, times the square root of the variance, the square of the standard deviation, divided by the sample size for each sample. Now, when we do a hypothesis test, we use these hypotheses. We might have a hypothetical difference called D naught. Now, D naught may be if we say we're baking in the assumption that there's an implicit difference. Is this different? And we're going to be testing, is the difference significantly different than this assumed difference? Generally, this will be 0, but, and you may see as such the null hypothesis done like this, and consequently each one is less than this difference, or is one bigger than the other, is one smaller than the other, or are they just not equal? I don't care which one you use, they're functionally equivalent to me, as I doubt we'll see any examples that actually have a baked-in difference. And the test statistic is just, oops, this is a mistake, should be the sample mean sample mean of 1 minus the sample mean of 2 minus this assumed difference divided by, once again, the variance of 1 divided by its sample size plus the variance of the other divided by its sample size and the square root of all that. And against a rejection criterion of T star alpha, or alpha over 2, depending which one, at a minimum, using the minimum sample size for the degrees of freedom, minus 1. So, Indiana Jones finds a tomb of 30 generations of Babylonian kings, each buried with 2 Sumerian slaves. In the artwork around the tomb, the slaves are depicted as virtual midgets compared to the majesty of the kings. Dr. Jones doesn't think the slaves are much shorter, so he examined the skeletons. The kings have a mean height of 1.6 meters, with a standard deviation of 0.5 meters. The slaves have a mean height of 1.45 meters, with a standard deviation of 0.3 meters. Is there sufficient evidence that alpha equals 0.05 that the kings are taller? So, now, normally you can designate, and you can designate either sample, right? We have 2 independent samples, the kings and the Sumerians. And we can designate one of them as 1, one of them as 2. And normally, it's not much of a difference, except in this case, we've been asked one is one taller than the other. So it's very important for our alternate hypothesis, which we're going to designate. I'm going to designate the Babylonian kings as population 1 and the Sumerian slaves as population 2. So we're testing to see, are the kings taller than the slaves? So the mean height of sample 1 should be bigger than the mean height of sample 2. That's what we're testing for. Now, once again, we're using a difference of 0, so it will simplify somewhat. So we have our test statistic T is equal to 1.6, the height of the mean height of the kings, minus 1.45 minus 0, divided by square root of the sample variance. We only have the standard deviation, so we simply square the sample standard deviation, divided by 30. We have 30 kings. And we add the sample variance, which is the standard deviation squared of the slaves. Now, there were 30 generations of kings, each with 2 Sumerian slaves. So 2 times 30, if each of them had 2, there'd be 60 Sumerian slaves. So 1.6 minus 1.45 is 0.15, divided by the square root of this whole deal is about 0.099, which will give us 1.5151 going on forever, which we're just going to call 1.52. So now we have to come up with our test statistics. So we have T star. It's a one-directional test, so we use alpha. We have to use the smallest sample size. We have 30 and 60, so we have 29 degrees of freedom. So let's go to the table. Once again, we're talking about a one-tailed test, alpha. We were looking at the 0.05 level of significance here, and we go down to 29 degrees of freedom, for 1.699. Our rejection criterion is 1.699. That is greater than 1.52. So what does that mean? It means we failed to reject H naught. So at the 0.05 level of significance, we do not see sufficient evidence. At the 0.05 level of significance, we don't have sufficient evidence to say there's a difference in height. There is no, any variation in height. The fact that this mean is higher than this is mostly due to statistical chance, based on our evidence here. So we don't have sufficient evidence to say that they actually were taller. So now we want to we took a sample of 16 men, 16 women, and 37 women, and tested and saw how many hygiene products they used per week. And we wanted to be, what range would you be 90% confident in saying women used hygiene products that many more times than men? So we want to develop a range of values with a 90% level of confidence. So we're talking about a 90% confidence interval. So our confidence interval takes this form: x bar 1 minus x bar 2 plus minus t alpha over 2 and the minimum, right? So we have n minus 1 degrees of freedom times this whole deal, the variance of group 1 divided by the sample size of group 1, and the variance of group 2 divided by its sample size as well, the square root of all that. So because it says women used hygiene products so many more times than men, I'm going to make females, women, group 1. I'm going to make males, group 2. So our mean for women is 6.7. Our mean for men is 4.2. Our variance, we only have a standard deviation, so 1.4 squared divided by 0.7 squared divided by 37 plus 1.4 squared divided by 16. Now, we have our T alpha over 2 n minus 1. This is the smaller sample size, 16, so we have 15 degrees of freedom. Our table, we go to the confidence interval, we set 90% at 15 degrees of freedom is 1.753. So 6.7 minus 4.2 is 2.5 plus minus 1.753. This whole deal simplifies down to 0.368 approximately, which tells us it's 2.5 plus minus 0.65. So our range is between 1.85 and 3.15. We can be 95% confident that women use hygiene products 1.85 to 3.15 more times than men do. One of the key assumptions required for those last groups of pairs is that they were independent samples. But what if they're not? Now, the t-distribution allows for what's called a matched t-test or a paired difference test, which means the populations are not independent. You have treatments that are closely related. Generally speaking, you match every single person from one sample to the other sample and can compare results that way. So what we do is we need to develop a new variable called d, which is the difference between each pair of elements from both populations. We'd find the mean, d bar, standard deviation, SD, and then calculate our test statistic. The null hypothesis is always that the mu d, the population mean of d, the differences, is always equal to 0. The alternate hypothesis and their critical values be handled identically to previous t procedures. And our test statistic is d bar minus 0 divided by the standard sample deviation amongst the differences divided by the square root of n. There's also a confidence interval, but we're not really going to deal with it. It's not often used. So here's a question I submitted for, and this isn't actually last year's final, but a few finals ago, but it was rejected, and I think it's a good example. So we have a maniacal mathematics professor, and he's convinced that raptors are the world's greatest mathematicians. So he gathers 10 random first-year math stat students, and actually, based on the sample information, we can see it's actually 6, and gives them a standardized calculus exam. Then he injects them with the raptor DNA, transferring them into prehistoric dinosaurs. Now he forced them to take another standardized calculus test in the raptor form, and then he gathers the results. And he wants to see is there significant evidence at the alpha equals 0.1 level of significance that raptors or Deinonychus are in fact superior mathematicians. So let's look at this. The procedures aren't very difficult for this one, but it is a little more grunt work. So our null hypothesis is always that the mean difference is equal to 0. Now the alternate hypothesis depends very much on how you construct the rest of this thing. So you can do it one of two ways. You can either develop your difference, your D is either dinosaur minus human or human minus dinosaur. But because we want to test to say dinosaurs are better, if you do dinosaur minus human, you would say that it's greater than 0. In this case, I'm going to just do it as human minus dinosaur to make the math just so it's a little more visually simplified. But then we're going to assume that we're testing to see if it's less than 0, it's worse. So 67 minus 75 is minus 8. 2 minus 13 minus 14 minus 16 and positive 4. Now, the sum of all that, the sum of our d's, is equal to minus 45. So because we're going to have to also develop the standard deviation, you can just use whatever process you find most comfortable with calculating standard deviation. You can subtract all these from the d-bar mean, square them, and do it that way. But I find it easier to use this formula, so I'm just going to go ahead and square them. You don't have to do it this way. Whichever method you find most comfortable for using the standard deviation, please go ahead and keep using that. But for demonstration purposes, because it's my preferred way, this is how I'm going to do it. So d bar is equal to the sum of d's over n, which is 45 minus 45 divided by 6 is equal to minus 7.5. Now our standard deviation of the d's, the formula I'm going to use because I have d and d bar, is sum of d squared minus sum of d all squared divided by n divided by n minus 1 square root of that, and that'll be equal to 705 minus 45 squared divided by 6, and minus 1 is 5, square root of all that, and that will get us to basically the square root of 73.5, which is approximately equal to 8.57, rounded off 2 decimal places. Okay here. So that was a lot of the grunt work, and after doing all that, and the construction is very important, but we do our test statistic, which is d bar minus 0 divided by sd divided by the square root of n. So our d bar is minus 7.5, minus 0 is still 7.5, 8.57 divided by the square root of 6 is minus 7.5 divided by 3.491, which is equal to minus 2.143. So what's our t star? We're testing in one direction, so it's an alpha with 0.1, and we have 5 degrees of freedom. So we go to our table. Once again, one-tailed test, so we look in one direction, 0.1. 5 is 1.476. Because our alternate hypothesis is less than, we take a minus of this, minus 1.476 is greater than minus 2.143, so once again we can reject H naught. We can say that there is sufficient evidence at the alpha equals 0.1 level of significance to say that dinosaurs are better than humans. And it doesn't matter how I chose to construct this. If you constructed it with dinosaur minus human, and those all became positives, you would just have to change your alternate hypothesis, unless your rejection criterion, but you'd find you'll still come to the same conclusion.